All right, I want to do some more work with graphics and metering especially. One thing I have here, which I've developed, and it's available if you want for free, is a VU meter ensemble for Linux. And you can see the microphone responding there. It's the left and right there for internal players like VLC and so forth, and there's a frequency spectrum up here which appears for internal playback. The microphone is just plain microphone. But as you can see, it's a meter, and the needles are going popping back and forth, and we can include arcs. You can see there the arcs are filled in, and the wide spectrum, narrow spectrum only applies to the frequency part, which I'm not doing today. Basically, I'm going to do the how to build a meter and how to build a resizable meter. I'm not going to get into the pulse audio. I might try another video on that. Pulse audio is fairly complicated. In order to access it, it's an unusual way of accessing. You don't call pulse and it doesn't return you something. You call pulse, tell it what you want, and give it the name of a function. Pulse queues up that function queues up your request for execution, and then when it's got the answer, it calls your function back. So you give a callback function to pulse, and it calls you back when it's got the information. And it can make it very complicated as a result because you're calling and you're not really getting anything back immediately. Another function is getting the answers. But anyway, so we're going to avoid pulse at the moment. So there's the meters, and there's a lot of things you might want to meter. I picked, for purposes of example, the load on the machine, and it's these are the 1 minute load, 5 minute load, 15-minute load, I think they are. It tells you how loaded the machine is. It's an indicator. It's not 100% accurate. I guess it's the OBS is chunking along at nearly 100% of one of the CPUs. As a quad CPU machine, if you type 1, you'll see all the CPUs in top. If you type 1 again, you don't see them. But anyway, so the CPUs are running about one CPU approximately is in use. Okay, what's the meter going to look like? And again, that's what I'm picking up. I'm going to be picking up that number of the 1 minute load. It's something. It's data. It changes. And this is what the meter looks like over here. It's very tiny. No reason why it has to be tiny, but I just made it tiny. And it's pinning the load because, of course, it's seeing OBS grinding away in the background. But anyway, it's draggable, and you can make it bigger if you are careful and you keep all the hash marks on it. It's peaking at 100% because of OBS, which is running, OBS and other things that are running are giving me what's a 100% load of one CPU. I can change that factor so that it would only show, a 1/4 load when one CPU is in full function. But there's a couple of things. Oh, it dipped back a bit. It updates every second. But the trick is here, two things. One, how to do the metering. And number two, how to make it expandable. Oh, it is dropping back. Okay, so that's what I want to get into. Now, normally when you have a window in GTK, if you resize the window, the children window resize themselves. But this window here is a drawing window. And the draw window doesn't like to resize. So you have to kick it a bit. And it is kind of difficult. It took a while to figure out how to do it. Now, if it's a regular window, for example, if we go to the pulse audio, let's see. There's the and that's the volume. That's the meter on the microphones, obviously. I don't know why it's got a difference between left and right, but it does. Now, this meter here, if I enlarge it, you see it gets larger and smaller down to a minimum size and automatically resizes because these progress bars or whatever they are will resize based on the parent. Now, if I go down here, they're not resizing because that's not a characteristic of progress bars, but they will widen if you tell them to. So that's easier to do. This thing with the drawing is a little more difficult, but that's what it basically looks like. Colors are optional. So how do we do this? Now go back over here. First of all, I've divided this up into two parts. First of all, meter. First of all, let's go into the Glade part. The Glade part down here is still calling it part1.glade. There's not much down here. what we've got, we've got a window. It's named window. It has doesn't have anything to it. There's nothing in particular. There's nothing I think that was changed over and above the defaults. It does have an event. It has on window configure event. This is a GDK event. GDK, D as in dog, not GTK, T as in Tom. It's D as in dog. It comes from the GTK when the window is reconfigured, when you drag the window around, when you try to expand or contract the window. So that's where I'm going to get the information on how to resize. It's going to be that event right there. There's no others, I think. Now, there's a couple others that actually you can grab, but that's the important one. In here, again, I don't think there was anything that got altered, that there's no packing. And let's see, there's a name, the title across the top, and otherwise it's resizable, of course. That's kind of important. But okay, so there's the window, and there's GTK fixed container inside it. It's got pretty much nothing. I think it's 100% default. I don't think I changed anything, and I'm pretty sure there's no signals down here. Let me see. These are under the widget signals, by the way. The previous one on the window level was under the widget signals. There's no, go back to here. You see they're under widget. Configure event is under the widget. It's not under the window. And then finally, the drawing area. Okay, now the draw area does have one signal. It's the draw signal. Whenever the system thinks that the window needs to be redrawn, it issues the draw signal. Now, the system will issue it for various reasons. If it detects some change and it thinks it needs to be redrawn, or if it becomes visible, as a variety of things. In the program, I queue up draw events. Every second, I grab. The way the program works, every second I grab the load for the previous second, or the load as it currently is at that time. It's actually for the previous minute. And when I grab that number, I then queue a draw event. So the system will say, oh, we need to draw the window. So the system will then send a draw signal, and we'll enter into the program, or the function, on draw to draw. I called it draw to because I pirated this from the other code. There were two windows. Draw 1 was the window with the frequency spectrum, and draw 2 was the window with the meters. That's why it's draw 2. There's no significance to the 2. I don't know, in fact, I was too lazy to change it to 1. Anyway, so that's there's the window itself, the drawing window. It's got nothing to it. It does have a position. It's at 0, 1. It's nothing here. Nothing unusual, but we do have that draw signal. So anyway, that's the GTK. It's minimal, and it sets things up. So all right, we got the GTK. Now we've got meter.c. Now the other one's going to be meter.h, and there's a bunch of include files. I'm not sure if they're all necessary, but well, I'm not going to worry about pulling them, because if you don't use them, they don't do anything. Okay, there's the three widgets for the window, fixed one, the fixed container, and the drawing window, and then builder, because we're going to bring this in through the GTK builder. There's a string called BG color, which is going to be the background, which, as you can see, is blue, and if you recall, it was blue. If you change it to one of the recognized words, you'll get other colors. I just left it as blue. There's the include meter.h, which is in the current directory, so it's surrounded by quotes. If it's surrounded by angular brackets, you're pulling it in from a system directory. There's the standard initialization. It starts off the GTK process and passes to it any arguments that were passed to the program. But no, I'm not using any, but it's just part of the ritual. There's where I get the pointer to the to builder from. It's coming in as a resource, resource.xml. Resource.xml has the code will be posted, of course. And it's just it just brings in the Glade file. There's nothing else in here. You could put icons in here and all sorts of stuff that could be used by the program, but in this case, I'm simply bringing in part1.glade, which is get out of here. Okay, so that brings in the resources. It means I don't have to read the file in. It's going to get it. In the process of compiling, you will compile resource.xml, and resource. I've done this before, so the compile here is compile.script. There is this glib compile resources. It takes in resource.xml, generates a C file. That C file is compiled, and it is incorporated into your program. So the things in the mentioned in the resource.xml become part of your program. They don't have to be read in from the outside. It's handy. And I've got an awful lot of libraries in here. Again, I'm not sure how many of them I really need. Oh, the Pulse library is in there. I'm not going to pull it out, but it's not being used at the moment. But it's a residue of the other program, which is where this all came from. Anyway, you can pull it out unless you want to experiment with Pulse, in which case try to get some Xanax first. Pulse is very, very upsetting at times. All right, so let's see. We connect the destroy signal for the window to onDestroy. It's a function that'll appear in the .h file. We connect all the signals with the builder. So there's only a couple of signals in the Glade file, but they get connected. We get the pointer to fixed one. We get the pointer to draw two, which are also named fixed one and draw two. Done this before. We unref the builder. We don't need it anymore. We say show the window. The window is defined because it came in up here with the the definition for the window came in with the GTK builder get object code. All right, GTK color. I declare something called color, and let's see, what do we do here? We've got the color. We do a color parse. GTK color parse. If it returns true, it means the parse worked. If it returns false, the parse didn't work. What do we pass to it? We pass the address, notice the ampersand, of the GTK color object. It's a structure. And we pass the string containing the color that we want to have established. It'll fill in the values in the structure. Now, if it recognizes the string color, which blue, it does recognize blue, it'll fill in the parts of color to make it blue. If it fails, you'll get 0 back, in which case I just set the color parts to 0, which means it's black. So you get a black background. Then I modify the background of the window with the color, again, passing the address of the color. And so that's how you got the blue background or whatever other color you want. I'm resetting the title. The title is also set in the Glade file, but this resets it again. I don't know what it is in the Glade file, but now it's meter 1.00. Set the window to be resizable. I think it was already set to be resizable, but it's now set resizable. You can set it to not be resizable, in which case it's fixed. And we... let's see, events. In order to get that GTK configure signal, you have to add the event to the window. So adding events to the GTK window, we add the GTK configure event. That allows the configure signal to come to the window. Otherwise, the window wouldn't get the signal, or not supposed to anyway. All right. In the meter.h file, there is a function called timer handler. You can see what we're doing here is we're telling glib, we're telling it that every 1,000 milliseconds you should call timer handler. And the null at the end means it has no parameters. I'm not passing anything to timer handler. But every 1,000 seconds, please, or 1,000 milliseconds, please call timer handler. And that starts the timer. So the timer is going to click every second. And then I call GTK main, and when GTK main returns, we're done. So we're into the program. Now, meter.h, this is where the actual program is. Again, I've got the include files in here. I decided to leave them because this may be useful to insert into other programs. So I just left them in there. They don't hurt anything if they're duplicates. There's a couple of things at the beginning. Show arc, which is global, is whether or not to show the arcs. If you have the needle rising and falling, should it show the arc, from the left-hand side up to the needle, the filled-in arc or not? I've set it to be 0, which is no. Load is the actual load that the timer is going to pick up from the system. and it's going to be the current load on the machine. And there's width and height. The initial dimensions of the meter are 100 by 50 pixels. There's also initial dimensions that were set up in the Glade file, which I don't know what they actually are, but these become the operative ones. There's the destroy. It doesn't do anything except calls GTK main quit. You could do things if you wanted to, but I'm not doing anything. Here's the timer. It gets called every 1,000 milliseconds. You can make it update quicker. If you're getting data from Pulse, you obviously want to update it more quickly. Showing the volume level once a second is a bit jerky. In the meters you saw, the volume meter, it was updating 10 times a second. 10 times a second, volume meters are jerky anyway. There's a delay at the beginning while it connects to Pulse. But you don't really see it as jerky as it actually is. And I've also got some averaging and dampening going on in the meters. The square box at the top here is the root mean square average. And that little narrow box is the peak, recent peak. And the needle itself is last couple of readings averaged. So it's updated every 1/10 of a second. So here we're only updating once a second because the load average doesn't change very often. Okay, how do I get the load average? It's in /proc/load average. It's part of your system. I didn't check to see if it's there because if it isn't there, your system is not working. So if I go to /proc is where there's a lot of system stuff. Cat /load. And there it is. Yes, there's the first three numbers are the 1 minute, 5 minute, and 15 minute. I think those are the time units. Load on the system. Excuse me. And then there's some, I forget what those other numbers are, but they load. There's a bunch of other things down there. So I open that so-called file. It's actually part of the system. I don't think there's not actually a file on the disk. The system provides you that information. I read it. I do an fscanf on it, and I read in &load past the address of load, and it gets me the first one. Fscanf will parse, and since the one it parses is the first one, and I close the file, because I'll do this at once a second. That takes almost no time to do it. Then I queue up the draw event. I tell GTK, hey, we want to redraw the window. And then I return true. If you return true, it means keep the timer running. If you return false, the timer halts. The timer will not be called again. So you can set up multiple timers. But if you have, if you have a timer and then once its usefulness is finished, you simply return false, and that timer won't come back again. That time event is killed. Returning true means it's going to come back. All right. Let's get down to the business at hand. This is where we draw the needles. Let me go down to draw 2. Here it is. This is the function that gets called to draw the meters. The function up above actually does the drawing, but here's where we come in from the system to draw the meters. And from the system, we get a pointer to the GTK drawing area, and we get a Cairo pointer. Cairo pointer is this is the drawing facility used by GTK and by Linux in most applications, I think. Okay, it's a pointer to the surface. I don't know too much of the details without going in and looking up what their nomenclature is, but that's your surface. Everything is going to be drawn to CR. CR is going to be in all the drawing functions, so the system will know where to do the drawing. Okay, we've got a couple of things, horizontal, vertical, and length. Because the meter, one of the things that makes it resizable is a couple of things, is the center of the meter, the center spindle of the meter. That's HOR, H-O-R, horizontal, vertical. That's the point at the center of the meter. And length is the length of the needle. So those two things, by positioning the horizontal and the vertical and changing the size of the length, you change the size of the meter. Everything else is dependent upon these guys. Okay, load is from 0 to 1. We're going to get the load we're going to get is between 0 and 1. Let's see. Let me find the load up here. Again, yeah, the load number is actually not 0 and 1. There's the problem. I just thought that is the problem. You get into your code. Where I said here the load is from 0 to 1, it really could be quite a bit higher. I was assuming only one CPU. So if it's only one CPU, you're going to get only one CPU unit, you're going to get from 0 to 1. You can have a single CPU and a load of 10, which means there's enough work to keep 10 CPUs working, even though you got one. This is a quad-core machine. Technically, it's fully loaded when the load is 4, when each of the CPUs is at full capacity. But the load takes into account other things like input, output, and so forth like that. So you can have a machine that's got 4 CPUs and have a load of 8, and all the CPUs are not necessarily fully occupied because it's doing a lot of input, output, and things like that, queuing stuff up. So I decided it was going to be between 0 and 1 would be the load. And that's not technically true. The number coming in from /proc/ load average can be between 0 and, I don't know, there's technically, I think, no upper limit. But I just said 1, and I set it up as 1. So if it goes over 1, it maxes out. So that's what you're seeing here. Sorry, I didn't notice it earlier. But I mentioned it when I'm looking at this, and I'm looking at the meter. There's the meter here, and you can see it's running at about 3/4. So what is the actual load here? The top shows you the same thing. The load is 0.65, and that's about where we are here. It's bouncing around a little bit. Now it's up to 0.868. So that's what it's showing. It's showing up to 1, but this number could be a lot bigger. And as a matter of fact, I can make it go bigger. If I run mumps, which is a computer language used mainly in medicine. All right, see the mumps has popped in there, and it's going to use 100% too. So it's using all of one CPU. Now you notice the load's creeping up. It's 1.20, 1.27, because mumps is just in a CPU-bound loop. See, it's keep rising. But the meter over here is pegged at 1, because that's as far as they let it go. If I wanted it, had wanted it to go larger, I could have, but let me get out of here. And we're back to the meter here, get rid of that. Okay, so I was assuming it would go from up to 1 only, and that's just for purposes of example. You could change it right here. Okay, so what it does is it multiplies load times mpi. Mpi is a built-in, it's one of the include define symbols. I don't know, probably from the math library. It's pi. That's all. So it's a double precision pi carried out to whatever number of places pi can be shown or can be represented as a double precision number, I gather. I have not looked at it, but it's pi. Okay, so load is being multiplied times pi. Okay, now look at this meter here. You see the right channel, it's pointing to the left. This location here is minus pi. Pointing to the left, flat on the horizon, that's minus pi. As you start adding to this value, the meter would rise and go over to the other side until we get to 0. So pointing in the other direction, pointing to the right, flat down, it would be 0. If you start going positive, it goes below the line. Seems like positive should be above, but it isn't, it's below. There are ways of changing the mapping, but then it just makes it totally confusing. But if we start going plus, we'd be going down, down, down until we got to pi over here, and then we'd flip to negative again. So a full circle is 2 pi, from minus pi all the way up to pi. So it's a minus pi to plus pi. It's a full circle is 2 pi. Pi r squared, that's 2 pi r is the circumference, that sort of thing. So this is minus pi. This is 0. That's the important part. It's the only part of the meter we're really looking for. So let me get this off the screen. And back over here, what I'm doing with this line here, as I'm getting a floating point value, by multiplying load, which I'm assuming is between 0 and 1, times pi. So in the case of 0, where the meter should be flat on the left, that's what it would be. It would be T1 would be 0. Okay, 0 times pi is going to be 0. When it's supposed to be pinned all the way to the right, and that would be a 1 in my case, even though the load theoretically could go much higher. But I'm assuming 1 is the max. When it gets to 1, the value of T1 is going to be pi. All right? Now, and this is where I clamp it here. If T1 is greater than pi, I make T1 equal to pi. This is where, of course, I would need to fiddle around with these things. This is the limit on the meter. This is flat to the right. If I went up here, which I wanted to modify load of, so the maximum load is going to be 4. I would say load divided by 4 times m pi, and then if it's a load factor of 4, it would be pinned to the right. And 0, of course, is always 0. But anyway, we're not really here to discuss load factors. The point is how to do the meter. And the meter is I need a value. And this value, T1, it's going to represent where the needle needs to go. The needle needs to go somewhere between flat to the left and flat to the right. Okay? Flat to the right is going to be 0 on the meter. I'm not there at the meter yet. I'm someplace else. And flat to the left is going to be minus pi on the meter. But my actual value of the that I'm going to be using the thing I'm going to be displaying is T1. I do check T1 so it doesn't go over pi. If it goes over pi, the needle will go all the way to the end and then down to the bottom. Looks kind of stupid. All right, so with that confusing explanation, basically T1 is the value I want to represent. And it's going to go from 0 to pi, which, of course, you know, it's actually going from minus pi to 0. But how are we going to do that? How we're going to do that, let me say it right now because we'll get to it later, is that when we go down to drawing the needles, we're going to pass T1. And we're going to add T1 to minus pi. So if T1 is 0, the position of the needle is going to be minus pi. If T1 is pi, the position of the needle is going to be flat to the right. It's going to be 0. So since we have to send the numbers down as minus pi, starting at minus pi and going to 0, and since what we want to represent goes from 0 to pi, we just add the two together and we get a value. Otherwise, I could do it without that by making the value we need to represent negative, and that just makes it confusing. So T1, I'm doing it in a positive sense, and I added to those negative pi's in order to get the value across the needle. I hope that's not completely confused it, but it works out. So again, if T1 is 0, meaning a load of 0, it'll be 0, and we add 0 to minus pi, and we make the needle point to minus pi, which is to the left. If T1 is pi, in other words, a load of 1, that is going to mean that T1 will be pi, and we add pi to minus pi, and we get 0, and that makes the needle point all the way to the right. I knew I shouldn't have done this. Anyway, here's the business where we start playing with the funny numbers. Width and height magically appear here. I'll bet you want to know where they came from. Well, they're coming from up at the top here. They were originally declared. There they are. There's my initial dimensions of the meter, 100 by 50. That's my size of the window for the meter. They get, I'm at the bottom of the screen now. I just did a Shift G. This is the configure event. Remember that? The configure event. So when you, as a user, grab the outer edge of one of these things and change its size, like I'm doing now, that's a configure event. If I move it, it's a configure event. There's a whole lot of things come in a configure event. But I'm more interested in the movement. I want to know what you've done to the size of my window. So the configure event will be invoked when you try to change the size of it. Okay, so it comes down into the configure event. It gives you the window who's being mauled or manipulated, which is of course, the window. I only have one window here. And it gives me a pointer to the event, the GTK. Notice it's D, not T. Okay, we come down here, we set some things, set those. Those are static, and they're going to be used to determine, they're going to remember the last value, and they're going to look at the current value, and if the current value is different from the last value, then we're going to do stuff. If they're the same, we don't do stuff. So that's what they're there for. Width, which is a floating, which is not floating point, I guess it's integer. We get it from the event variable e and configure.width. The event variable, or the event pointer, is pointing at a structure, and the structure's got lots of parts to it, one of which is the width of the window, the other which is the height of the window, and a whole pile of other stuff in that structure. And you can go sort through it under GTK, under GTK events, and you'll find it, and there's lots of stuff, but I'm only interested in the width and the height. What did you do to change the width and the height? So I extract the width and the height that you've altered it for. Now here's a little game. I'm asking if the width that just came in from the event is smaller than the previous one. This W will be the, you see, just before I leave, I make W equal to width and I make H equal to height. Okay, so they record the values that were, and these will be the values that are. And I'm basically saying, is the new value less than the old values? And then I'm subtracting 5 pixels from each. As it turns out, this was a lot of trial and error to get this thing to work. And when you try to shrink a window that's got a drawing surface in it, a Cairo drawing surface, the Cairo resizes pretty slowly, and it's kind of in slow motion. And I found out if you just encourage it, instead of going down 1 pixel at a time, give it a little boost. 5 pixels is not a big number. Make it go down by 5 pixels. And then the user doesn't really see how slow it's running. Look at it again here. Here is the thing. And when you're enlarging it, it enlarges pretty quickly. Bingo. You have to keep when you're enlarging, it's your problem to do the ratios. You could calculate the ratio and force the thing to be exactly the correct ratios. I wasn't interested in doing any trigonometry. So in other words here, if you make it too narrow, your meter is going to be distorted. But nonetheless, the trig part is easy enough. But when I make something smaller, you see it here, it's actually, if you look closely, it may not be showing up on the recording, but it's actually a little jumpy a little bit. But, the 5 pixel jumping, you don't even see, well, you're even enlarging it, you're seeing you're seeing some jumpiness too. But if those guys weren't in here, if these -5s, it would be shrinking very slowly. So I discovered that if you add a little kick to it, it's going to be more responsive. I was going even higher, up close to 10, and you're really not all that noticeable. It's a little more jumpy at 10. So in other words, if you're shrinking it, if the new value of width and height are less than the old value, which kind of implies you're shrinking it, then you want to give it a little extra boost as you're shrinking it. It'd probably been a good idea to check I didn't go below 0, by the way. Nothing really happens if you do. Just get a warning message in the background. All right, then I remember the old. Here's where I remember the values that we're leaving with. And then I hit it with a size request. There's a lot of different ways of changing the size. You can hit it at the window level. You can hit it at the fixed level, fixed one, at the container. I'm doing it at the GTK drawing window level. That's draw 2. There are different ways of asking for a size to change. I'm not going to get into them. You'll see them if you go hunting through GTK window widgets resizing. This is the request you want. Some of the others will lock the window. This is the one you want. So anyway, I'm just basically telling it, okay, I want you to resize the draw window to width -4 and height -4. The -4 is allowing for the boundaries of the window. The drawing surface is in the window, but the window has decorations around it. There's a way to remove the decorations, by the way. It's called X-prop. But anyway, we're not doing it now. It's a system command. But anyway, so the -4s there are to allow for the decorations on the edges of the window. Otherwise, the thing when it draws the drawing surface, it'll be too big to fit in the window, and the window will get bigger, and then the window will get bigger, and you'll get into a cascade. So the -4 works. All right, so where are we in this nested configuration? The timer clicked. The timer collected load, the current load. The timer invoked the draw function, or queued a draw function. the draw function comes down and is going to draw the window. Simultaneously in the background, any configuration events have come in and they've set width and height. That's what we were going for, width and height. So I move back up here where we were in the draw function. There's the mystery of where width and height came from. And what I do here is I readjust HOR and horizontal and vertical. I'm just using abbreviations. These are the central points in the spindle. Okay, and they're going to be based on the current height and width. The width minus 10 it leaves for margins so that the needles doesn't go right to the edge. You divide the width by 2 because the spindle or the center point of the arc is going to be in the middle of the screen. And I added 4 again. That was just to shift it a little bit from the left-hand margin. This was done empirically. You can fiddle with these numbers and you'll get some changes. This is, of course, where you would be putting any trig functions to ensure that width and height have been properly adjusted. Actually, you'd probably put them down here. You wouldn't this size request. You want the width and height to be corrected at this point, so that they'll be the correct ratio of width to height to match them the desired width and height, which I didn't do. I'm not going to, but you could do it down there to ensure that you get the right thing. Okay, vertical is the height. The length, I just empirically, again, I just kept playing with it until I saw one I liked, minus 35. So the height of the box is 35 is height. The length of the needle will be 35 pixels less than that. Again, this you may want to adjust this because if it's bigger or smaller, you may want to make some changes. But anyway, that gives me the 3 parameters I really need, which is horizontal, vertical, and length of the meter. Then I call needles. Needles is the guy that's going to draw the picture on the screen. And I pass down to its CR. The CR came in here as we mentioned before. It's the Cairo drawing surface. It came in with the draw to draw signal. I pass that down. I pass down horizontal and vertical. Vertical minus 20 is to allow 20 pixels beneath the meter for a label. Okay, so when with the vertical on the screen, it starts at 0 and it increments going down. So minus 20 means the center is going to be higher than it's going to have room for 20 pixels because I put a label underneath it. If you noticed, it said load. It's in the next 4 lines. So that's what that is. Then the length, and I pass down T1. T1 is between 0 and pi. All right, when I get back, there's the label. I move to a point, and again, the horizontal minus 25 was eyeballing it until I got something I like. You may want to make that adjustable, but it seems to be good in all cases. And it's a little, it's up from the very bottom of the screen of the drawing surface, and it writes out CPU load and strokes it. So again, if we go over here, you can see it again. There it is, CPU load down at the bottom. And it's always the same. It's always the same size and the same distance relative to the relative to this central spindle here, or whatever you want to call it. That central point. This is HOR, VER, horizontal, vertical. That's them, and this is underneath it. And there's my gap underneath them to allow for labeling. All right. All right. So now we're ready to go down to needles. And in needles, we've got the drawing surface. We got the coordinates of the in the drawing surface of the central point of the graph. We've got the length of the needle and the thing we want to graph, T1. All right, now we go back up here, and this is actually not too complicated, although it really looks it. Drawing the meters. Let's see. Here's where I again fix it so it's not going to go past the limit and all the way in needle pointing straight down or something. So if it's greater than pi, make it pi. So that limits the what we're going to draw. We're going to draw hash marks. Those hash marks you saw here. All these hash marks going up and around the screen. They look big when the thing's small. They look smaller when the thing gets bigger. But there's long hash marks and short hash marks. I thought they looked nice. That we're going to draw those. that's the first thing we're going to draw is those hash marks. And the hash marks color themselves in, again, that show up? Yeah, it doesn't really show up too well against the background here, but above the meter, these are gray, and behind the meter, they're yellow. Okay? Against the blue background, it doesn't really show up, but these guys are gray, and anything prior to the needle is yellow. If we change it to red, it might be more visible. Let's change it to red. Well, I think it's going to be more purple, but anyway, red, green, blue. Now, yeah, you see it's a little more visible. I think it's a little more visible. Maybe it's not. I have no idea if the recording's picking up this. Obviously, they're whitish or grayish over here, and behind the meter, they're red. Again, you can... that's where you change the color, and the color numbers run between 0 and 1 for red, green, and blue. And so at 1, that's max. At 0, it's minimum. So that's max red, minimum blue, and a little bit of minimum of green, a little bit of blue. All right. So red, green, blue. Okay. This is now the trick to doing the hash marks is I'm going to go through a loop. And the loop, every time it goes through the loop, it's going to increment. We're going to get a point. We're going to get a value, which is where we are in the arc. And it's going to start at minus pi. And we're going to increment it a little bit each time. And as we do, the meter will be, or we're going through the meter. We're not drawing the needles. Yeah, we're just going to draw hash marks. So x is going to be the amount that I increment. So we'll start off with minus pi, and we'll go down to 0. And in process of doing that, we're going to go across the arc. Okay, and it's going to be 1/20th. Actually, we're going to do it 21 times because we're doing the first and the last as well. So it says, but the increment will be 1/20th of an arc. And where's the 1/20th of an arc? There it is, right down there. That x is equal to x plus pi divided by 20. Okay, since they're both constants, there's no danger that that'll have been done during compile time. But we're incrementing x by 1/20th of the arc, and that's x starts off at 0. Okay, so we're going to draw, actually we're going to draw 21 from 0 to 20 because we start off at the beginning and we end at the, we're drawing one extra. All right, setting the, if x is beyond t1, in other words, if we're drawing a hash mark which is beyond where the needle will be when we paint the needle, then we want to switch to gray. Well, they're kind of a light gray. They're 8, 8, and 0.8, 0.8, 0.8. Those are the hash marks that are gray, or they look more closer to white on the screen if you notice. Long hash marks. Every other hash mark is a long hash mark. Okay, so I just do I modulo 2, and if it's 0, then it's a long hash mark. So these are this group here. This group here is the long hash marks. This group here is the short hash marks. Okay, it's the same code, but here these are the long hash marks. These are the short hash marks. So every other hash mark will be long, and every other one will be short. These could probably be blended into. Well, I don't know. It's probably better to leave them as two separate ones. How are we doing the hash marks? Well, here's the trick. We tell Cairo to draw an arc. An arc on the drawing surface. I said every one of these functions is going to have CR in it. That's the drawing surface. The center of the arc is going to be at horizontal and vertical. Again, let's bring this guy up here. The center of the arc is going to be here at the center thing. All right, so there's the center, and we're going to start over here, and we're going to draw an arc. We're not drawing it, which is invisible until I paint it. We're not actually going to see an arc here, but the system is internally seeing an arc. So I'm saying there, create an arc with a center at horizontal and vertical, whose length is, from the center, is len, L-E-N, length, plus 10. Length is going to be the length of the needle. I'm making the hash mark to begin to be out there at the length of the needle plus 10. So what we're doing is we're telling it to draw an arc out here. See, here's the needle. The needle ends right here. These hash marks go 10 pixels beyond the needle. This is length, L-E-N. This is length plus 10, this point out here. the furthest point on the hash mark. All right? So what we're basically telling the system to do is to envision an arc and that goes up and around like this, that is 10 pixels beyond where the length of the needle will be. Okay, and how far will the arc go? Well, the arc is going to start over here, and it's going to go up and around to minus pi plus x. X initially is 0, so the arc is, it's no arc really. It's just a point out here. As x gets incremented 21 times actually, the secondary point on the arc is going to move further and further across the screen. Okay, so initially it's x is 0, and then the next time x is going to be 1/20th of pi, and this is where that's where it is actually. So the second time through, it's going to be minus pi plus 1/20th of pi, which means it moves up because it's moving towards 0. This is 2/20ths or 1/10. This is 3/20ths. This is 4/20ths. Okay, so every time I do this function right here, I'm changing we're going to do this 21 times. We start off here and we building short arcs until eventually we've got an arc that goes all the way around. Now we're not drawing needles, we're just drawing the hash marks. So anyway, I've created an arc that starts here and goes someplace around the circle. And how much around the circle is determined by x, because minus pi is all the way to the left, and minus pi plus x will be someplace further to the right. And finally, x will equal pi, and then it'll be minus pi plus pi, and it's 0. So it'll be all the way to the pointing to the right. Okay, so we now get an arc. It's not on the screen. It's just mentally the system knows there's an arc. We ask Cairo for the point at the end of the arc. So envision in there, the system has drawn an arc out to here, internally. It's not on the screen. And I ask for the point. It's going to give me this point right here where the cursor is pointing. So that's the furthest point on the arc. And I notice I'm passing ampersand, so I'm going to get the address of the, passing down the address of the variables. And I got to do them twice here. There's the first one, x and y, and down here it's x1 and y1. So it'll come back x1 and x and y and x1 and y1 in the next line. We'll come back with the point, that coordinate point out here. You're not seeing an arc, but if there were an arc, it would start here, it was visible, and it would go, let's say, out to here. And what we're going to get, when we ask for the point, we get the point of the last point on the arc. All right, so I've got one point. Then I do it again. I said, let's do an arc, but this time it's only len. It's not len plus 10. So it's going to be the inner mark here. Okay, this is length plus 10, and this is length, just plain old length. So, and we get that point. So these 2 points, x and y, and x1 and y1, differ from one another by, of course, it's going to be angled, and so I'm going to by 10 pixels. So I get 2 points. Nothing's been drawn yet, but I now have 2 points. Now I want to draw. So I say, let's create a new path. Let's move to x and y. Let's draw a line from where we are, which is x and y. Draw a line to x1 and y1. So I just drew this hash mark. That's the hash mark, because x and y are the outer part of the hash mark, and y1 and x1 are the inner part. I just draw I'm told to draw, and when I stroke, it actually draws you actually see the thing on the screen. So that stroked out a long hash mark. Short hash marks are the same, except rather than be 10 pixels long, they're only 2 pixels long. You can change it. And this one is, the short hash marks actually don't go to length, they go to length minus 1. I don't know, it's anything you want. But these are short hash marks. They're 3 pixels long, and these are longer hash marks. They're 10 pixels long. So that's how the hash marks get written. And then at the bottom here, each time we increment x, so we move further and further across the arc. And at the top here, we check to see if our x has gone above T1. If it has, we're going to change the color of the hash marks. They now shift to gray or whatever color you want them to be. Okay, hash marks are drawn. Now I go back to now I'm back to the needle itself. Set it to yellow. That's yellow. And we're basically doing the same thing. We're asking for an arc, starting at the center. There's the center. It's going to be length long, and it's going to begin at minus pi, and it's going to go to minus pi plus t1. T1 is going to range between 0 and plus pi. So when T1 is plus pi, you're all the way over to the right. When T1 is 0, you're all the way over to the left. So there's the arc. Now remember, we're creating an arc. We haven't actually drawn an arc yet. We get the current point down here. We're doing really the same thing as above. We're getting the point at the end of the arc. Okay? And we are drawing a path, creating a new path. We're moving to that x and y. And we are drawing a line from the center point, horizontal, ver, out to that point. There's your needle. And stroke it. That's how the needle gets drawn. That's the needle. Show arcs. If that show arc parameter is 1, it's presently 0, you will see you'll see an arc filled in. Let's do it here. Whoops. Show arc. Make it 1. Some people like this. I don't particularly like it, but I've been told people do like it, so left it in there. And there you can see there's the you're seeing the arc. It's filling in the arc. It's filling in the arc. All right. I don't particularly like it, but there it is. And we'll go down the bottom. I'm going to turn that off. Yeah, you've seen it. That's all you need to know. But anyway, down at the bottom here, filling in the arc. Filling in the arc is because some magic happens. And this is a quote from the documentation. If there is a current point, an initial line segment, not visible, will be added to the path to connect the current point to the beginning of the arc. The current point from up above is HOR and VER. The last point we did was this one right here. That here, you see it, HOR, VER? That's the current point. Because then after that, when we get down here, the current point at this instant, we get down here, is that guy. And we're going to draw an arc. This is the thing that draws the arc, starting at minus pi, going up to pi plus, okay, there's your, that's where we drew the arc. That's where we created the arc. It's the same as up above. The arc is there, and we draw a line from. So what I'm saying here is that in this create Cairo arc here, it's not only creating the arc, but it's drawing an imaginary line from the original, what was the current point, which is horizontal and vertical, HOR, out to the arc. So there's a hidden line over on the left-hand side going out to the arc. All right? And then I draw the arc, which goes so far across the screen, same as the needle, to the same extent as the needle. Then I draw a line from the center going out. That's the needle line itself. Then I fill it. Well, what's it going to fill? Well, let me bring it up again. What it's going to fill, again, I've got these things, is that the first arc here went from the central point out to here, and it drew an imaginary line from here to here. Then we arced over, okay, to here. Okay, then we got an arc that we can't see. It goes all the way around up to here. Then we drew a line from here to here. So in the system, it sees a line from here to here, an arc going up around here, and a line from here to here. Okay, so it sees an area of arc, and the fill fills this area in. Again, this is this obscure quote from the documentation. When I do this arc down here, and I create the initial arc, it automatically adds a line from here to the starting point of the arc. When I get to once I've done the arc and I get I create a line from the central point to the edge of the arc, okay? Because the current point here becomes the end of the arc. But anyway, and then I've got a line here, I've got a line here. They're imaginary. Line 2 actually does create a real line when I stroke it. But that's the area that's being filled in. That's how it knows where to fill things in. I'm sorry that's confusing, but go look at the documentation, Google for that quote, and you'll get into that. You can be confused on your own. But that's how it does the arc, and if show arc is available. And then down here it does something very similar to create that central spindle. It creates a 4-pixel wide arc, which goes full circle. It goes from minus pi to plus pi. It goes minus pi all the way to 0, and from 0 all the way up to plus pi. So it's a full circle. And it creates, of course, there was initially a line from the starting point, like above, and then we create a line to the new point, which is actually the same point because it came full circle, and then we fill it in so you get that spindle in the middle. Let me compile this again so you could actually see the spindle. The other one didn't quit. All right. Yeah, see that spindle? I thought a spindle would look nice in the center. You could make it a different color. If you didn't like yellow, let's make it a different color. I don't like yellow. I want to make it red. Let me get my color stuff down here and pop it in. And let's make it red. Or purplish. I won't go any further. Then you want to change the color there. Whoops. Yeah, now you see I've got a red spindle in the center. Okay, and that was the color that was, when you get back to the other function, that's the default color. That's you can change the color to get CPU load is in the same color because that spindle was the last thing drawn. Okay, so I hope that wasn't terribly confusing. I'll post this code. It's it's a pretty good example because anytime you want to do any kind of metering, this is how you do it. If you want to have nice circular meters and so forth. And they can be full circle, but I just assume you wanted to have a half circle meter. That's the more standard kind. But it's fairly straightforward. But the thing that's is the resizing, which a lot of people want to do. You can the resizing will work with other things, but anything you do it with, you have to have control of it. Now, when this GTK event occurs, of course, I am going to, I go in there and I readjust, recompensate the width and the height, and more work could have been done. I could have done some trig functions to make sure they got compensated, so the entire meter would always show, so that you can't do something like this where, see how it went small there? Now you're only seeing part of the meter, but the concept is there. Drawing windows are difficult to resize. They don't like to be resized because there's a lot of pixels involved. But there you've got a load meter of sorts, and I use that to create the VU meters. And actually, is mostly the same code. The code for the VU meters is there as well. The trick is that the actual size of the meter is dependent on the number in LEN. Everything from the central spindle out to wherever it goes, the meter really sizes on LEN. Now, in the case of Pulse Audio, we get the data from Pulse Audio, and as I said, that's a series of callbacks. You call Pulse and say, who are you? You call Pulse and say, I would like to have the address of let's say the microphone. And you call Pulse and say, well, when you get microphone data, would you send it here? And then every so often, Pulse sends data, and it activates your function, sends data to it, and you've got to go pick it up. So it's more complicated, but it's the same idea. Then when I get the data, I'm now sampling it 10 times a second. I smooth it a little bit, and I run it up as a meter. So I hope that was useful. It was certainly longer than I wanted it to be, but sometimes things are longer.